Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
A little slow on the uptake here. I got it though.
No, you're
Sorry,
good.
I was looking up some equations and all sorts of things because we have a billion questions.
Yes, we do. And welcome to another episode of Ask Something about electrochemistry. Let's just get started because
Yes,
a lot of people have been asking questions, and let's
it.
take care of it.
Yeah. Thank you, everybody.
Thank you.
Welcome. Thank you for joining us. Let's jump right in here. So Pourbaix had some questions shortly ago, an hour ago or something. So chronologically, I believe her questions are first. So let me jump right into this. So she has said, let's say we have, it's the first one. I think it's from bottom to top. Yeah. Okay.
Yeah,
Good. Just
I
making
think
sure
so.
my order's right. Okay.
Yeah.
So she says, let's say we have two electrodes, A and B. All right. A shows better currents at lesser voltage, and then B serves to be the best catalyst for OER based on LSV data, ideally looking at the LSV data. All right. One will expect electrode A to have better ECSA values compared to electrode B. Is this assumption true? Or even B can show higher ECSA? So there's a second part of the question. I'll read through all of it, then maybe I'll talk about it.
Yeah.
Now let's assume
a lot of parts.
Yeah, exactly. So number two is now let's assume A is showing more electrochemical active surface area. If we normalize the currents with respect to ECSA rather than geometric area, electrode B will show more current density than A. Can B be called the best now for OER? Isn't this result the opposite of the first scenario? And then if electrode A is best, so impedance bit of this, is it always necessary for electrode A to show smaller diameter of the semicircle or lesser charge transfer resistance in the Nyquist plot? Yes, no, and yes. Okay, there's a lot here. Let me try to break this down here. All right. So there's two electrodes, A and B. A is better current at lesser voltage than B. And so that means it's a better catalyst. All right. So let me just, I'll try to, let me bring up a drawing a little bit here. There's a couple of things to just sort of, I guess, point out, and I guess sort of as it relates to your question, but you're talking about OER. So we're talking about positive voltages or potentials here, right? So if we're looking at oxygen evolution reaction, let's just say we have catalyst A and catalyst B, right? Let me make sure I get which one is which here. So you said the beginning here was that A shows better current at lesser voltage. Yeah. All right. So broadly speaking, let's just forget about A and B for a moment. Let me just talk about two sort of phenomena as it relates to the oxygen evolution reaction. So if we're doing the oxygen evolution reaction and we have one curve that looks like this, right? What we're looking for are two things simultaneously. One is, let's say this is 1.2 volts. That's roughly the potential of the oxygen evolution reaction. Okay. We are looking for where is it's not exactly clear, but where does it start to uptick here? So this would be the overpotential, right? So that's one metric. So there's two metrics that we're looking at for the most part when we're looking at how effective is a catalyst at doing anything but OER in this specific case, right? One is, okay, well, ideally it would, shoot up right at 1.2 volts or whatever, but maybe the catalyst doesn't. It shoots up at, 1.4 or whatever this value is. So the overpotential is the onset potential, how effectively it does that. Now the second is usually some metric, and again, I always just make up numbers for this because I don't know specifically what the appropriate numbers are, but usually what people are looking for is at let's just say like at 1.5 volts versus an HE or whatever. what is the current? And so that's another metric. So it'll be like I, or the current density, which would be J, at 1.5 volt. Again, I'm just making up these numbers. The actual numbers might be, whatever they are based in the literature or what have you. The point is that the two metrics, for example, that you're looking at for an OER catalyst usually are the overpotential at which it starts doing the reaction, and then the current density at a certain.
Isn't it like when the current density is 10 milliamps? What's the voltage?
Oh, that too. Okay, right.
Yeah, I was thinking
you're probably right. So, okay, maybe that's okay.
Something like that.
So, yeah, so it's either or. You might be right.
Yeah.
It might be the other way. So it's either the current at some voltage or at
like some people use 10 milliamps.
Yeah, 10 milliamps per centimeter squared. The potential is what? Right. Okay.
Yeah,
so
something like
but
that.
it's like one of them is sort of just like, when does this start shooting up in current in doing the reaction of interest, and another is a quantitative metric. The point that I want to bring about this, and I'll try to hopefully get into the question or analyze it a little more thoroughly, is that you have sort of two possibilities, I guess. You could think about it this way, right? You could have, if this is again 1.2 volts for the OER, like where it happened, you could, for example, have a catalyst that has a really great onset potential, right? Okay. So this is where it starts going up, and it's like, this is my over potential here, right? It's like, it's this distance, and it's like really small. So it's like really great, small onset potential. It does it, but the current doesn't actually go up that fast. On the other hand, you could have a catalyst. I'm going to draw it offset just so you can see. Let's say it has a much worse over potential, but it might have a better current response. So this over potential is bigger, but it quickly eclipses in current the red catalyst. So like what I'm saying is that I don't know that these things are necessarily always correlating. In other words, the thing that has a good over potential or one metric definitely has a great, and the other metric not necessarily. Okay. So broadly speaking, to your question, I think this means that it's possible you can have like one catalyst that in one manner of analysis is, quote unquote better, and then in another in a different one is better in another way. But now let me just again kind of read through your question again and kind of, I don't know, try to think it through here. So so in this case, what you have here is that A is better current at lesser voltage, right? So in the situation that you're describing, it's probably a little more cut and dry, right? So now let's try to draw and think through your specific system again using A and B. So you're saying that A has better current at less voltage. So like A is doing that and B is not as good or something like that, right? So the onset potential and the current. So for any particular voltage, right, whatever this voltage is, the red one has a higher current than the blue one. That's what I believe you're saying, right? Jump in, Alex, at any point if you see something, whatever.
No,
I think
that's right. I
understanding.
think we're totally on to
yes,
it. Right. That's the situation.
That is the situation. I think so. Okay. And, so basically you would expect electrode A to have a better ECSA value compared to electrode B. Okay. So that's where you're wrong, right? So here's the mistake that you're making here. This is raw current. I should label my axes because I'm a good scientist. This is current, right? Current is proportional to surface area. If you were, but you're actually making your own point. The electrochemically active surface area is how you sometimes plot current instead. If you could plot, you could transform this axis to J, which is like milliamps per centimeter squared or whatever microamps per cubic kilometer, square kilometer, whatever. It's surface area based, right? When it's if one way, for example, to accomplish this plot would be to have much more physical area of A than B. So if the surface area of A is greater, even much greater than the surface area of B, then your raw current will be higher. And in fact, what might happen in this situation is that if you were to like zoom in on just the B and look at what that shows, you might actually find that the B actually does uptick a lot. It's just that in comparison to A, it looks like it doesn't, right? You know, in other words, at a quick glance, the overpotential for A looks like it's right here, right? And the overpotential for B looks like it's like way over here. It's like worse. But the reality is that when you zoom in, it's actually here or even next to, it's at the same place. It's just that there's a surface area mismatch. So what you're actually, your question is kind of answering itself, I guess, is, I don't know how to put it more elegantly here, but like, if you, this is why you have to normalize the current in these kinds of comparative studies, because the raw current means nothing. You can get 10 billion amps, but it's because you have a pickup truck full of catalyst. If you have a ton of material, the amount of material on the surface area of your material is proportionate to the amount of current you get. But it's like, well, that's not useful. I can't put a truckload of material into a tiny little supercapacitor or cell or something, right? So the point is you have to normalize it. And so you may find that your assumption about which was better changes when you normalize to the area. So I think it is critical that you normalize to the area. Now, you sort of have gotten to, if you normalize with respect to ECSA rather than geometric area, this is a tricky one because it depends on how you calculate the ECSA. I've talked about this a number of times in various live streams. I can talk about it more. I won't now for the sake of time. We have a lot of questions. But for instance, if it's a platinum catalyst, we sort of have the very popular, commonly used, I'm not going to do it. I'm just drawing it for the sake of completion here. But you have this kind of platinum CV here. Right. And so you're basically using this hydrogen desorption, hydrogen adsorption surface area. You're using this region, which has 210 microcoulombs per centimeter squared. So you're basically, with platinum, it's like a really easy, well-documented, studied method for calculating the ECSA. If you don't have that and you're using something else, it might be like, I don't know precisely how you're calculating ECSA. You might be doing it with like microscopy or something like that. So I do think it's possible to get different answers, whether you're normalizing to ECSA or geometric area. That could certainly be something, and I don't know how to speak more to that. You should just make sure that your ECSA calculations are accurate and correct, and things are done. But pick one, surface area and go with it, I guess, is kind of all I can say about that. And then the last part, and then I think we'll move on here, right, is that you've talked about basically Nyquist plots. Basically, the charge transfer resistance ought to be proportionate to the overpotential, or inversely, sort of. So similarly to how I described, where the overpotential is or whatever, depending on the how zoomed in you are or whatever. In theory, whichever one has a better onset potential, I guess, ought to have probably a lower charge transfer resistance. But this will probably also depend on, to a certain extent, the surface area, because you can also normalize Nyquist plots based on area. So again, you're going to be in a situation where if you take Nyquist plots and you're trying to get charge transfer resistance of both A and B, you will probably find differences if you don't normalize to area, because the impedance is current
voltage over current.
Voltage over current, yeah.
Frequency dependent voltage over current.
Voltage over current. Yeah, V,
yeah.
V equals IR. Yeah. Anyway, the point is, because again, you have raw current here, your impedance will be different. It may be different. if you don't normalize this to surface area. So if you do normalize it to surface area, then in theory, again, you could have the right like order of which one's better or which one's not. And that includes the charge transfer resistance, because when you normalize your axes, like you have this much RCT, right? This many like ohms, but until you normalize it to surface area, it actually ends up being this much, like because this is like ohm centimeter squared or whatever. Once you normalize it, you get a different number, and then they'll match or not match. So the point is, I guess, that you want to make sure that you, again, sort of, I don't know, follow your advice here, like normalize stuff to the surface area. That gives you an appropriate comparison. And just, the trickiness, there's a trickiness for sure with related to ECSA or geometric area. Just pick one that you're comfortable with, or that you feel you have accurate like values for, and use that for everything. Just, if you're not maybe confident that the ECSA is easy to calculate, reproducibly across different catalysts, just use geometric area is my suggestion.
Mm-hmm. All right. Very good. So I'm just going to go in the order that I think they show up on YouTube. Meliodas60 said, in your recent video about Warburg, you showed how to visualize the semi-infinite diffusion Warburg. Can you tell us how to visualize a Warburg short and Warburg open as well, please? Yeah, sure. So I'm glad you saw the video. That was good. This is how I think about it. And this may be a little bit more of an exercise as well. But so I think about, and if you haven't seen the video, it's probably helpful to watch it. But you have the semicircle, and then you have your Warburg line, your semi-infinite diffusional tail Warburg, and you have Z real, you have negative Z imaginary. And so what I'm going to do is I'm going to try to draw kind of like if I do a different color, if you have the same type of thing, for the visualization regarding the Warburg open and Warburg short, and I haven't like perfected this per se, but you may get something that looks like this. I think this is the Warburg open short. I always get those two confused. And then if I do blue, for example, if I have a blue one, sorry, make that thicker. It follows the same thing, and then actually in reality it goes out like this. But what you're looking at are these kind of two differences. You have these differences in this region. And in my video, I described the real impedance as being like approximately kind of like the distance the electron has to move, or the charge has to move. So this is, this is distance. Let's see, distance. And the imaginary can be thought of as time. And so when you have a straight 45-degree angle, this is equivalent to a molecule that has to move through some semi-infinite diffusional length. And so at these very low frequencies, this is like omega is very low, it's like having a very long distance and time for the molecule to move. So that's how I describe the semi-infinite diffusion. So what about the case when you have the Warburg open, which is this guy, right? I always get these two confused. Short. I mean, the red line. Well, this is typically a case, there's like two situations where you end up getting this. Physically, this is a situation where there's some kind of layer, some kind of like thickness of a redox active layer, right? So there's some kind of porous membrane, if you will, on the electrode surface, and it's filled with a redox active molecule. I take that back. It's not that it's filled with this redox active molecule, it's that it's very easy to exchange between this layer and let's just say it's an oxidized species. It's very easy for oxidized and reduced species from the solution to get into this layer. So initially what ends up happening is in this, you have most of this is the same, right? You end up seeing that you have this kind of usual diffusion, Warburg diffusion, 45-degree angle behavior. And that's the same behavior as, well, the molecule has to diffuse from some distance. Let's say it's here to the electrode surface. So the molecule has to diffuse from here to get to it. And it takes a certain amount of time for that molecule that, remember, this layer doesn't have any of the redox species inside of it. It only gets it from here. And so everything here is normal. But we end up getting this curving down, this red curve, when in comparison to the normal semi-infinite linear, diffusion, this represents having like a lot of time, for example, right? This is representing the case where like, oh, my molecule is actually here in the semi-infinite Warburg case. But my molecule doesn't have to travel nearly as far to get a redox molecule. It can get the redox molecule from here, right? Because this is basically full of your redox species, and it's easy for the molecule to go here and move to get it. So it's as if it has all of this distance and all of this time. Really, it has all this time at this point. But because it only had to go really this far, it has excess time. And so on the time scale here, let's say, we're looking at here or something. Actually, we're looking more like here. On the time scale, well, it doesn't need that much time. It only has to go to this distance to get the ion. It has so much more time to get it that its imaginary impedance is low. Its imaginary impedance is low because compared to the semi-infinite Warburg, it would have to get a molecule from way out over here, because this is where the diffusion layer would normally be. But it doesn't have to do that. It has to be right here. So that's how we think about it. At these low frequencies, where we almost have no imaginary impedance, this is the case where this is really the case where like the molecule has so much time in comparison to my infinite diffusion that, well, on the time scale of the experiment, the molecule's already done the work. It's already done it. It doesn't need to go. And that's why you can keep going slower and slower and slower. And you just have this kind of set resistance value based somewhat on the film thickness. So no matter how slow you go, it has excess time because it's as if it was given this amount of time, but it only got, and I can't draw straight lines, of course, but but it's been given all this extra time where if it didn't have this porous membrane, it would take a super long time for it to get it, but it really has extra time. I don't know if that makes a whole lot of sense, but that's how I think about it. When you compare the Warburg open and the Warburg short from a distance and a time aspect, it's like, oh, well, because of how this membrane works, the molecule has lots of time, but it doesn't need it because it can get the molecule from a shorter distance. And so it's like, it's just chilling on the scale of this experiment, which is very, very low because it's low frequency. Now, on the other side, which is the Warburg short open, I never remember whether it's up or down. But in the blue case, in this case here for the blue, this is the situation where I have, this is typically used when I have an electrode and my redox, and I only have a redox active molecule inside a membrane. I don't draw membranes very well. And I have nothing over here. So there's no redox species here. This is the case that you maybe usually get with like a battery or sometimes like a some kind of like this is a boundary layer where the redox molecule is not here. So in the beginning, on the time scale of diffusion, where, and if I use like a red dot this time, like from this point, it acts exactly like my semi-infinite, linear diffusion. But once I reach this point over here, that's where we start to get what's kind of like a capacitive current in a way. And I no longer can move charge because I don't have any charge. There's no charge in this area. So it's as if I was given lots and lots of time, but I couldn't deliver the charge because there is no charge beyond this membrane. So that's why I end up getting, as I go to longer and lower frequencies, longer and longer times, the molecule, it doesn't end up, it's as if I'm waiting for that charge to come back, but it's just taking forever because the charge isn't there. I told Jimmy, hey, go grab me 5 pounds of potatoes from the grocery store. Jimmy goes, but there's no more potatoes. So I'm just waiting. This is just my time waiting for Jimmy to come back from the grocery store, but there's no more potatoes.
Oh, Jimmy.
Poor Jimmy. This situation over here is like the grocery. I told him, hey, I gave you 15 minutes to go get me some potatoes from the grocery store. But he's like, bro, I got a place that's like 5 minutes away. So like I can get the potatoes and be back with extra time. Like on the time scale you told me to get the potatoes back, like I'm already there. It's done. Because you gave me 15 minutes and it took me 5. So that's how and it's not about Jimmy and his potatoes, but like literally molecules carrying the charge are moving and dropping them off at the electrode where your charge transfer resistance is doing the thing. So I've spoken for enough time. Hopefully that helps from like understanding the Warburg open and the Warburg short in comparison to the semi-infinite linear diffusion, how we can kind of think about these things rationally from this same model.
I really like this. Time is the y-axis, distance is the x-axis. It's definitely a simplification kind of a thing.
Yes, it is a simplification.
I love that explanation, actually. I really do. To just give you kudos, because it really helps you kind of understand like more physically what you're seeing in a Nyquist plot, because Nyquist plots are the ones that's like imaginary, real. What does this mean? To a lot of people. So to me, it's like a demystifying. All right, we're going to move on because we have 8 billion questions. You guys are wonderful. Thank you for joining us. We want to do justice to your questions. I want to let you answer Paul Mining's question.
Oh, yeah, sure.
It's another potential window one that you've answered before. But before then, I will just answer this one here. So Meliodas had a couple other, which was internal reference, asking about the internal reference potential. Is it the equilibrium or a formal potential? I'm not sure what it seems like. What's that in reference to? Internal reference.
I think some of the order of the questions we got kind of scrambled. Somehow, so he had some questions like he was talking a little bit earlier about like if he's using an internal reference for my electrochemical analysis, say ferro-ferri solution, does the potential of my reference change with respect to pH and concentration?
Yes.
Yes.
So the Nernst equation dictates that.
Yes.
A potential will change at roughly minus 60 millivolts per pH unit. That's simply Nernstian. You can do the mathematics out basically of like the H plus and OH minus dissociation. But basically, every 10, it's the same phenomenon where every 10x change in concentration results in about 60 millivolts change, just because it's a logarithm of the reaction quotient in the Nernst equation. And so similarly, pH changes do that. It's inversely related to pH. So like as the pH goes down, the standard potential shifts up and vice versa. Okay. But yes, the potential will change based on pH and concentration, as again is dictated by the Nernst equation. And when you add an internal reference, wherever it is, you shift the axis so that it, like usually this is done with non-aqueous with like ferrocene, and ferrocene happens at what, like 0 or 0.1 or whatever.
Oh, we just call it 0.
Yeah,
whatever it is.
Wherever.
Okay, right. Wire.
Right. So you add some ferrocene into your thing, and you're a non-aqueous, so you're going from minus all numbers approximate 47 volts to plus 63 volts, and right at 0 is where the ferrocene duck happens. And then at 92 volts, you're finding your special little thing happening, right? Okay. I'm obviously just being silly here, but the point is, if the ferrocene happens at 500 millivolts, you just move it You subtract 500 millivolts on the x-axis. That's it, and you line it up, and that way you get and it might move from test to test, from scan to scan. You just shift your axis so that the ferrocene always is at 0, and therefore you have a comparison to know, okay, well, my thing happened at whatever reasonable number, like 1.2 volts or something, but it was 1.2 volts away from 0. So if it happens at 1.4 and the next time, but the ferrocene happened at 0.2, well, it's the same difference. You just shift it, and then you know what your voltage is. So that's what we mean when we say internal reference, usually. And then this one is another one that you've actually talked about, Alex, before, as it relates to basically the Butler-Volmer equation, but probably the Nernst equation too, because it's always the Nernst equation.
It's always the Nernst equation.
In CO2 reduction to form methanol, the equilibrium potential is minus 0.38, and someone's doing chronoamp at minus 0.2 and getting methanol. Is it possible? And basically, how is a faradaic process occurring in a non-faradaic region? Well, so there's a fundamental misunderstanding here. And it's something that I'm guilty of personally. I say it this way very often, and as electrochemists, we tend to talk this way. And I just talked about the onset potential. Well, it has to happen after that potential. So you're commonly going to practically think that, well, if minus 0.38 is the standard potential, well, I'm not going to get CO2 reduction until I go more negative of that. And that's for the most part true, but it's not technically true. So yes, it is absolutely possible to get reduction or oxidation before, quote unquote, the potential, the actual potential. The Butler-Volmer equation, if you look at the Butler-Volmer equation, and I can probably pull it up because we have it in here somewhere. Nope, in design in here. Let me pull it up as I talk. There it is, Butler-Volmer equation. So there's two terms here. There's a C ox and a C red, right? Basically, these are just giving you the contributions from both, and they're based on the overpotential, which is the E minus E0 term. But without belaboring this too much, the point is, even if you are at a potential negative or positive of the E0, you're still going to get some current, let's just say, of that reaction, just not a ton. It really starts to push exponentially, according to the Butler-Volmer equation, once you get like well beyond that point. But yes, it's absolutely possible to get some methanol when you are approaching that. I mean, like there's, if you were at like positive 0.6 volts and you were getting methanol, well, I don't know how that's happening. But when you're getting pretty close, yeah. And you can even, the last bit I'll say about this, and then we're going to again move on, is you can even think about it practically. Like if I'm doing a CV, I mean, you ought to be able to think about this yourself intuitively. If I'm doing a CV, right? And that's not straight at 0, right? Okay, whatever. And I'm scanning negatively, and I'm going to get a peak. Okay. And then I'm going to scan back, and I'll get a positive peak. Right? Okay. And this is my CV. Well, where's the E0? Well, we commonly refer to the E0 as halfway between these two peaks, right? So we could say that the E1 half, which is roughly speaking, the E0 is right here. Okay. Well, think about this yourself, right? This is, let's say this is the minus 0.38 that you said, just to use your exact example, right? Okay. Well, even look at my own example at minus 0.2. Let's say that's right here. Even on the CV, I've already started the increase or decrease, whatever direction you're talking about, of current has already started to happen. Even in a CV, we observe this. We don't think about it very often, but we have current for the reaction that we're studying before we reach the E1 half here, or the E0, roughly speaking, whatever you want to call it. So you observe this happen a lot, actually, and you just don't think about it. But this is the exact point, is that yes, you are actually doing the reaction, just you're really hypercharging it once you get beyond, and that's why we typically pick a chronoamperometry out here. So we're really driving the reaction, mostly irreversibly, whatever. Right. But just think about it in terms of a CV. You might realize again that, yeah, you are getting some current even before the quote unquote faradaic region or the E0 number.
I would just add one more thing to that, which is I studied some CO2 reduction stuff in grad school.
Mm-hmm.
It's a good chance that the result is nonsense. because
So everything I said is wrong.
Well, no. I mean, what you're saying is still correct. Like when you have a CV and then, you can have potentials that are off from the E naught and still have a reaction.
Yeah.
But
for CO2 reduction,
for CO2 reduction, carbon dioxide to methanol is a 6-electron, 6-proton reaction. So it's kinetically super, super difficult. And so from that and like methanol, there's like quite a bit of methanol like in the lab. Someone maybe cleaned the glassware with maybe a little bit of methanol. And so how are they detecting the methanol with some GC and stuff? Like carbonaceous contamination is all over the place. So I think it's fair to say that you're right. In some cases, it really might not be possible in some cases where like, if you were doing any other reaction, I'd be like, yeah, it's definitely possible. But like the only thing to add is that CO2 reduction, which is notorious for contamination issues, it may actually be a false result from whoever's doing the study. So
interesting.
Just be wary of that.
Helpful that you've done that.
Yeah.
In graduate school, you would know some of those intricacies that I have no clue.
Yeah. Good. I only add that small bit. Paw mining.
Yeah, I think that's next.
Okay, so we're gonna go to paw mining next. We're getting through these. So I just want to double check the order.
Yeah, I think it was the voltage limit or the upper and lower. Yeah.
Yes. So if I have three electromaterials and I perform LSV, how to interpret the LSV data and tell which electromaterial is best for oxygen reduction reaction? And how do we find the onset potential for ORR?
God,
we literally just talked about this. How do we select the upper and lower voltage limit for the LSV experiment? So I am going to defer to Neil's previous, like just literally like go back in this video if on YouTube. It's the first thing Neil talked about.
I'll just draw this for the sake of your specific question.
You don't have to draw it. You just have to go back up.
Well, no, because that was an oxidation and ORR is a reduction. So this is very different.
Yeah, yes.
It's not.
It's just the other. Yeah, it's just the other.
The reality is you're just going the other direction. So the oxygen evolution reaction was positive at 1.2.
Yeah.
The oxygen reduction is just going the other direction. So the oxygen reduction reaction, what you're looking for is something like this.
Yeah.
Maybe it flattens out if you're doing RDE, but basically the onset potential is subjective. This is the tricky part, right? It's that this is 1.2, 1.23 or 22, whatever volts. This is the E0 for ORR. OER is just the same as ORR, but the other way. Okay. Oxygen reduction is hence the reduction part of it. And you're just looking for, I don't know how people do this. There's different ways that people do this, right? So it's like the inflection of when this starts to drop. How do you calculate that? I don't know. Take the derivative and figure out where the derivative changes. Look at the concavity. There's like no correct answer necessarily, but you're looking like, oh, well, this starts to dip down here. And so my over potential is 50 millivolts or whatever this is. And so my onset potential would be 1.15 volts, whatever. This is sort of just an example of how you would do this. That's the fundamental kind of a thing that you're doing there. And then whatever, all the rest of it is what I talked about before. How do you determine what's best? Again, to repeat my previous argument, normalize it to the area, whether it's the electrochemically active surface area or the geometric area, but you want to normalize it. You're going to compare with literature for, basically what voltage do you get 10 milliamps per centimeter squared or 50 milliamps, whatever the metric is for ORR, for specific things. You can do stuff like that. You can get the impedance, area normalized impedance, and compare it with other researchers and determine. And then the only other kind of test I didn't talk about before that people will do with ORR, for instance, is like is a stability test. So you'll scan over and over and over again, like 1,000 times, and see if it still looks the same, or does it lose activity over time? Does its onset potential change? Does the amount of current you get decrease? Because if you're studying ORR, it's for probably a fuel cell application or electrocatalysis application, and it has to last, for some amount of time before it deactivates or what have you. So those are the general ideas, I guess.
Yeah, and you can just go to bigger voltage windows if you're getting a lot of activity or not a lot of activity.
Yep.
So continuing on the discussion of OER and HER and everything about hydrogen. Tool, you asked this question last week. We didn't have a chance to get to it, but in a water splitting reaction in a 3-electrode system in alkaline media, could we explain the water splitting reaction specifically?
I was looking up these potentials. I have these.
Oh, okay.
To do. I know.
Yeah, sure.
Hogging the questions here.
Yeah, no, it's all good. Because in alkaline, it's interesting in alkaline versus acidic media.
Yeah.
The reactions change. You have like OH. In this case, you have OH minus is the prevalent species compared to H plus. And if you're in acidic, systems, you're going to have H plus and you're not going to have OH minus.
Right. And the standard potentials are different. So the overall difference is the same, but each individual one is different. Water splitting, alkaline. So I'll just sort of write out the equations for you here. I guess. I mean, if it's helpful, I know it's oversimplified, but the oxygen. So water splitting involves the oxygen evolution reaction. I should just do this text box rather than typing. Oxygen evolution reaction. There we go. All right. So the oxygen evolution reaction in alkaline media is it's 2H. Wait. Sorry.
Yeah, so it's 2 OH minus.
2H minus. Yeah, I got it. 2H.
Yeah, I was thinking about this question before.
There it is. Yeah, I got it. O2, H2O, and 4 electrons.
Yeah.
Yep. It's 4 OH minus. Yeah.
4 OH minus. Okay, yeah, 4 OH minus.
Yeah, not 2 is 4. I got to get the right number of electrons.
Yeah. Unless you want to get like a fraction of an oxygen.
No, that's
to come
weird.
out.
Yeah.
Which always feels really weird.
4 OH minus gives you 2 water.
Yeah.
Plus O2 plus 4 electrons.
Yep.
Plus 4 electrons. And this has an E0 of like 0.8, 0.4. What is it? It's 0.401. E0 is 0.401. And then the hydrogen evolution reaction is the other one. So I will again make a text box, save myself. This is the hydrogen evolution reaction. This is the coupled other one for water splitting. And that one is, I have it. It's minus 0.8.
Yeah, water.
It's water plus 2 electrons. Yeah. So H2O plus 2 electrons gives me, it's like OH 2 hydrogen plus 2. It's 2 of these.
Yeah.
2 hydrogen plus or OH minus.
Yeah, so just 1 hydrogen.
And one hydrogen. One hydrogen.
And
yes. Yeah. There we go. Oh. I can't really erase.
Yeah. It's hard to erase these.
plus 2 OH minus. There it is. Okay. Yeah. The stoichiometry is fine. Here we go. Okay. 4 hydrogen. Yeah. 4 hydrogen. 2 electron. 2 oxygen. All right. Perfect. All right.
Yeah.
So that is the hydrogen evolution reaction, and this one has an E0 of like 0.84. What is it? 82 minus 0.83. Okay, so when you do the math here, hydrogen, so that's the reaction.
You'd flip the bottom reaction.
Right. So you get 1.23 again.
Yeah.
Basically. So the point is it's the same as the difference in the acidic one. It's just that in the acidic one it's easy because it's like 0 and then 1.23. Mm-hmm. Now it's 0.4 and minus 0.8. So they have different individual reaction pathways and they have different individual E0s, but the difference is still the same when you're looking at these one and compared to the other. So so anyway, I mean that is, without getting more specific, you just kind of asked what the reactions were. I guess that's sort of the direct answer to your question.
Yeah,
these are the water splitting reactions for alkaline media.
Yeah,
directly speaking. So follow up if you want any more, I don't know, discussion about it, I guess. But for now, I'll kind of leave it there, I guess.
Yeah.
So,
all right, moving on, getting through them. Tech Science asks, how can I draw my Cottrell lines from a chronoamperogram? So I don't know if there's a term called Cottrell lines, but what I think you mean, it's kind of close to like an Anson plot, sort of say.
it's like t to the 1.
Yeah, you're just plotting the current versus the square root of
time.
1 over the square root of time.
1 over, yeah, 1 over.
So let me add another slide. But you get your, and here's kind of an important minor caveat, I would say, about doing this, just to make sure you get good data. So you have your time, and then you have your current, and then you get some, and then you get the spike, and this is 0. And basically, you want to kind of exclude some of this data. You want to exclude some of this early data. It doesn't have to be that much. And you want to exclude some of that data as well. You don't want these because they contain data points that are not completely Cottrell-like. And what you'll do is you will plot the current. You'll just take this data, and then you plot it versus t to the minus 1/2. And when you do that, you should ideally get a straight line, and that's like your Cottrell line. Sometimes this is referred to as like an Anson plot. I think, pretty sure it's called.
Yeah, I think it's an Anson plot. Yeah.
But that's what you would do. And if we go up to, because I have the Cottrell equation, this is the Cottrell equation, and you're just plotting the current versus 1 over the square root of time, and this whole thing plus the square root of pi becomes your slope. And ideally, a bunch of the things like n, a, and then you can solve for things like the diffusion coefficient or the concentration if you're making a calibration curve type of thing. But that's how you do it. That's your Anson plot.
Yeah,
or Cottrell line. Okay, moving on. We got go through them.
Well, we're getting here, everybody. Thank you for bearing with us. Cigar has, let's see what this is. Oh yeah, there we go. So aluminum foil connected as a working electrode, silver chloride as reference, platinum as counter. Using a neutral electrolyte, I tried to sweep the potential from 0 to -1. Bubble forms at -0.1 in both. What is the reason?
Counter and working.
So you are in neutral electrolyte with a silver chloride as the reference.
I think we need to know what neutral electrolyte is.
Well, I'm guessing you mean just like pH 7. I mean, I don't know. You have like salt that doesn't make it appreciably acidic or basic. I'm guessing that's what you mean.
Mm-hmm.
So, I mean, I guess the only thing I could think of in general is that at like 0 volts versus NHE is the reaction for hydrogen evolution. So in theory, anything less than 0, you could be generating bubbles.
Mm-hmm.
Now, there might be something else going on. For example, you have aluminum foil as your electrode. If you have a lot of it, maybe there's a lot of surface area there. And so there's a lot of possibility for generation. I don't know if the aluminum itself is dissolving. Aluminum...
it's usually aluminum oxide. Could you be reducing the aluminum oxide?
Yeah, but why would that make bubbles?
It's just a lot of current, and you'd be reducing the oxide to oxygen. Maybe. I'm guessing. I'm literally like,
so Al, like it's like Al 203
203
basically, but that's alumina. That's not.
Yeah.
I'm not sure what the oxide is that forms on aluminum foil. Like if it's Al 203, Al 203 is like alumina, and that's an insulator.
Yeah.
It's actually like, it's what they make ceramic materials out of. So it's not electrically conductive, but maybe in a small oxide layer it is. I don't know if it's like precisely, because aluminum is +3, oxygen's -2. So it's Al203. I'm just thinking out loud here. I know that as another sort of tidbit of information is that aluminum metal, like metallic aluminum metal, is extremely reactive. And one of the reasons why you don't get that kind of problem when you use aluminum foil is because it has a oxide layer like that forms naturally in air.
Mm-hmm.
And so perhaps Alex is right. If you're reducing the oxide layer when you go to negative potentials, or even any kind of moderately negative, let me look at what the while I say this, what is the reduction potential, for example, of aluminum? So possibly that's something that's happening. I don't know. So that's probably not the right aluminum reaction. Let's see. I'll just click through some of these aluminum ones. Aluminum 3+ to solid aluminum happens way more negative than that. That's not it. This table doesn't have. It's probably not in here because aluminum oxide is an insulator. Like I said, it probably doesn't really have a. I guess maybe if you did Gibbs free energy, you'd figure it out. But anyway, I guess that's kind of my two possibilities. I would say, for example, is perhaps that you're reducing some oxide layer, revealing metallic aluminum, and I think metallic aluminum will react in water and release hydrogen gas chemically, not electrochemically, in the same way that like a metallic alkaline or alkaline earth metals will react in water. Mm-hmm. I think you'll form aluminum hydroxide and hydrogen gas. I think that's a thing that can happen. So that's one possibility.
Here's another possibility.
Yeah.
Double check your reference electrode.
Well, that too.
If your silver chloride's blocked, even if you're trying to apply a very low voltage,
it might actually be a crazy voltage.
It might be trying to apply a crazy voltage,
whether high or low,
or a crazy current to get the voltage.
Yes.
And that's why both sides are bubbling like crazy.
I was taking the approach that nothing is broken, but something might be broken. So that is
something might be broken.
So that's a good point. So check on the state of your electrodes with that. So if it isn't a broken reference electrode or something of that nature, not connected properly, causing the runaway, I think it's either that you somehow are producing native aluminum metal that is chemically reacting, which it can do with water, or it's just that I know that it's like minus 0.1, so versus silver chloride, you add 200 millivolts or something.
Yeah, it's about 200
so you're actually slightly above zero. Anyway, you're on the verge. I don't know if it specifically makes a ton of explanation, but I think it's possible for one reason or another, depending on, you have a slight pH difference, maybe that pushes the potential up a little bit. Okay. That you're just doing hydrogen evolution. That could be it. I don't know. So again, either something's broken, aluminum metal itself is reacting with water and that's producing a lot of bubbles, or it's just the hydrogen evolution reaction, which can happen at potentials negative of 0. And I don't know. Maybe I don't know if aluminum is like just a tremendous hydrogen evolution.
Yeah, he has some more information there. The AL takes very negative potential. Yep, that's what you said.
Okay.
Not rechargeable. So
HER is occurring at the working electrode, and OER at the platinum. Obviously at the platinum you'd have the alternative reaction. That could be it. So okay. So thank you for clarifying, Melia, about the AL2O3. That one I it was not positive. Whether that's happening or not, if there is any, I think it is still possible. If there is any native aluminum in the aluminum foil, which I don't know if that is, but if there is some amount of aluminum, pure metal, maybe that thing. Although I don't know, because you can just dip aluminum foil from your kitchen into the sink and it doesn't explode. So I don't think necessarily that's it. So
not so sure.
Yeah,
double check the reference.
Those are double check the reference electrode. Those are the things that we can think about here, I guess, right off the bat.
So. Yeah, right off the bat.
Okay.
Let's scroll back up.
I think Tapan is next.
Yes, Tapan is next. Tapan asks, hi, I want to know if I use same material for anode and cathode in H cell, BPA at anode and O2 at cathode. May I use 1 molar KOH at cathode, or I have to take PBS? For power density plot, what program I have to run in Autolab M204, please suggest. I don't know what PBA is. I mean PBS.
Well, BPA is
BPA.
bisphenol.
Oh, bisphenol.
I
Okay.
think it's a polymer of some kind.
Mm-hmm.
It's that one that was like banned from all the like water bottles.
Oh yeah.
Because it was
Okay. Okay. So
I'm
that's
guessing
the
that's
same
what it is. And
molecule.
then PBS is phosphate buffer solution.
Okay, phosphate buffer solution. Okay, so he's using some buffers in H cell.
I don't see why you would be precluded from using anything at the cathode. Why would you not be able to use KOH at the cathode? I'm not sure why you would. I don't know what so you
Mhm.
seem like perhaps you're under the impression that you ought not to use KOH at the cathode and you have to use PBS. I guess so. Part of this is that I don't know. For instance, maybe are you worried that does KOH do something to BPA? Is part of it? I don't have any experience with these polymers or these chemicals specifically, so I'm guessing maybe that BPA doesn't like survive an alkaline or something like that, and so you're hesitant to use KOH even at the other electrode. All I can say in some general sense is that when you're using an H cell, it will necessitate mixing of some sort slowly between the anode and the cathode side. So it is conceivable if, for instance, you have you could do this, like it's possible. You can have acid on one side and base on the other side. And it seems like, well, why would I do that? They can't mix, they'll bubble and neutralize or whatever, but you can. And then over time, there will be some neutralization that occurs. And the danger, for example, of this kind of thing, when you have, thing at anode and thing at cathode and they're incompatible, is that where are they going to mix? In the frit. I mean, that's where they're going to meet first, right? If they meet, slowly diffusing one way or the other. So it's like if there's some sort of reaction chemically or whatever that happens between, BPA and base or whatever, it's going to happen in the frit, and maybe that produces bubbles, maybe that causes frit blockages. Like those are the dangers in some general sense. But I just don't know otherwise what the reason would be. I don't know intimately the compatibility of like BPA.
Here's a comment.
Yeah.
Actually, when I'm using KOH, I am not getting the proper power density plot.
Check the potentials, because if you're in KOH compared to a phosphate, what's the pH of a phosphate buffer solution? PBS pH. Is it 7.4? Okay, so a phosphate buffer is pretty neutral. So check the potentials that you're at, I guess, is the first quick thing to be sure of, because when you go from PBS at about 7, pH of 7, to 1 molar KOH, which is about pH of 14, you're going 7 pH units up, and 7 times 60 is 420. So the potentials that you would expect to see stuff are going to be shifted negatively by about 400 millivolts. So make sure you're in the right potential window. Make sure you're shifting your potential window appropriately. pH goes up 7, potentials shift negatively by about 400 millivolts. That's how pH works, as we talked about before. So that's the one quick thing I would double check. Otherwise, I don't know how much more I can exactly speak to as your specific system. If you're not getting specific results, I don't know 100%. Alkaline is not working as well as a different electrolyte. There's obviously, very probably some chemical reason or electrochemical reason for that, and I just don't know enough to speak to that. And then finally, of course, we can't really answer the question about what to do in Nova software or Autolab software. That's not our company. I don't know how to use to program with their software. I'm sorry, I can't help you. You're going to have to speak with someone either at Metronome or another user who knows how to use their software. So yeah, we can't unfortunately help you too much with competitors' software programs. So
yeah. I think, let's see. Pourbaix has a comment from, I think, earlier.
Okay. Yes.
Just saying, we calculate ECSA by performing CVs at different scan rates, and then calculate the CDL, and then ECSA from it. Is this method ideal for ECSA calculations? And then I guess, is it always expected for a best catalyst to show a high ECSA value?
Generally, so I'm trying to answer this.
It's such a weird thing because in principle, the electrochemically active surface area should not have anything to do with the activity, but
right. What it's going to affect is the downstream practicality, which means if I have to put 10 kilograms of my catalyst into my battery or my capacitor for catalyst A, but I only have to put 6 milligrams of catalyst B, well, I'm obviously going to pick catalyst B because I need much less mass, right? And the only difference is the ECSA. So,
I guess. Okay. So here's my question, which is that everyone here is basically using like a platinum catalyst. So it's not. So are the people talking about like, oh, my catalyst is very good because of the fundamental chemistry that I have some neat molecule that makes the reaction go better, or it's like, no, we're really all using the same fundamental catalyst, which is a platinum atom or a platinum cluster, and maybe the platinum atom or cluster is a different size. That could change the chemistry of why this thing is different.
Different crystal facets.
Different crystal facets based on their synthesis procedures. So
it's like it's just I'm trying to handle the subjective terminology of like better and best.
Yes. Yeah.
It's like, yes, in general, better ECSA means it's better or whatever.
Higher,
but it's what you said. It's like, yes, it for the same material, right?
Yeah.
Whatever. You can put platinum, for example, in a polycrystalline disc or something like that, and it will have a worse ECSA, like per volume, per mass, per amount of platinum than a platinum on carbon, where the platinum molecules are small little nanoparticles, where there's more surface area active. It's got a better ECSA, but it's the same material. It's the same reaction. It's the same, let's just say it's the same crystal face.
Yeah.
Maybe it's not exactly, but let's just pretend it is. But it's like, yeah, one's better because I get to use less of it to get the same, like it's got more surface area for the same mass. So I get more current out of it. So I get to use less of it. It's more efficient. It doesn't drive up the weight of my system. So it's like, yes, but we're hesitating because it's like, I don't want to be like always the thing that has greater ECSA is better. It's like, well, maybe it's just the morphology or your synthesis procedure is better. It doesn't necessarily mean the material intrinsically is better, like kinetics wise.
Yeah.
It might be the same. Or even worse.
Yes.
You know,
right?
Which is the kind of the point I was trying to make, where it's like, you got to normalize stuff because then you'll, by area. And I, the CDL thing to get the surface area, I think that's possible, I guess. You could do what, I guess, scans and
the non-faradaic region.
Yeah, as long as there's nothing faradaic happening, I mean, you can sort of.
And some people used. I've seen some people like use the capacitance value, and then there's
you have to find a normalized value to relate it to.
Exactly.
Which I don't know what
and there's some weird literature value, like, oh, for water it's this, and then they then they get some.
So yes, in general you could, but like you're getting CDL, so you're getting the CDL one way or another on your material. But that's okay. So that's like farads, or millifarads or microfarads. You have some amount of farads. Well, to get the surface area, you need to have some literature value of like farads per meter squared.
Yeah.
And then you do a division and you get the meter squared or the centimeter squared. So it matters where you get that.
Yeah, what that
value is, and the conditions of your CDL that you got are the same or similar enough to what was in the literature, what person. So there's definitely some things there to be cautious of. Like, okay, well, I just found some random paper where they said, 2.7 farads per square meter for nickel. Okay, well, that's its specific capacitance. Under what conditions, for what type of material? Like, just make sure that what you're using is related to the literature thing that you did. And then in general, yes, you probably can make that kind of relation.
Yeah.
So just be cautious about that, because it's easy to just be like, take a thing from literature and be like, I got what I needed. And it's like, make sure that it's applicable. You know?
Okay. Moving on. We got
we're getting near, everybody. Thank you
Santiago.
for your questions. We'll see you.
Santiago, good to see you, I think, again. How can electrodeposition be performed in a 3-electrode cell? What technique is required, and what is the electrode configuration? Generally speaking, for electrode deposition in a 3-electrode cell, you have your 3-electrode cell. You'd put a electrolyte that contains the ion of what you're trying to plate, what you're trying to deposit. So maybe it's nickel, maybe it's silver, something like that. And then you would apply. There's 2 ways of doing it. I have usually recommended you do a constant current experiment, and you actually, it depends. You can always, there are many parameters to adjust, because constant current means that you're depositing at a consistent rate, basically. Now, in the 3-electrode system, normally you have like a small planar disc electrode. So it's very easy to plate that with like just a little bit of current. But if you have like a big, large surface area electrode that you're trying to plate, then it could take longer. You may have more current, and the issue ultimately becomes something like mass transport. So normally it's diffusion limited, but you may put like a little stir bar in your solution to make sure that you get fresh nickel, silver, whatever you're trying to deposit to hit your electrode. I may do something like a CV experiment just to see at what potential do I get silver deposition. Also, what potential may I get stripping. Once you plate something, you can strip it off. So I would find the potential with which it happens. You can also set the potential. Say like, oh, it's at maybe minus 0.6 volts is where I want to be at. And that will guarantee that you're continuing to deposit that material. But it doesn't guarantee the rate. The rate could change, how quickly. So most of the time, people just plate by setting a constant current, how fast you want the reaction to occur. And then you'll monitor the potential. And when the potential starts to change dramatically, you know that your reaction is over. That's usually for bulk electrolysis. But that is usually how it's done. So chronopotentiometry is the technique you would use to do electrodeposition. So let us know if you have any further questions about that. But we're just gonna try to get through.
We skipped over reactives questions.
Oh, we did. Oh, I'm sorry.
Yeah, we got to Pourbaix there. So reactive asked a question: how to determine the number of battery cells in series and parallel for an electric vehicle with a specific voltage requirement in a battery management system? Should I try to have a close V to devices V? I'm not sure what that last part exactly means. Basically, the needed watt hours. So there's 2 parts to this. The first is if you have an electric vehicle with a requirement of X volts and X amps or whatever, right? X volts and Y amps, whatever. I mean, for the most part, it's simple math, right? The voltage adds in series, the current adds in parallel. So, I mean, again, this is if this is too rudimentary for you, apologies, but just as the first sort of thinking this through in a very simplistic way, if you have batteries that have, let's just make round numbers here, 4 volts and 1 amp hour capacity. That's easy, right? And my vehicle needs, 20 volts and 10 amp hours total. Okay. I'll get to the energy part in a second. Well, very clearly I need to have 4, 8, 12, 16, 20. I need 5 S and 10p. So it's 50 batteries. It's 5 in series, 10 in parallel. So like, I mean, this is just simple math, right? Like this is very easy, simple math. You might have a little extra to make sure you're eclipsing that. Maybe you'll have 6s, 12p, I don't know, whatever. So to a certain extent, it's just making sure you add the math. So when you have batteries, I'm drawing resistors, I don't know what else to draw, right? in series, voltage 1 plus voltage 2 plus voltage 3. You're adding up the voltages, but I equals it's you don't add the currents. And so if you have a lot of this, right, in parallel, so it's like this is like a 3 by 3 or whatever. Then you have V1 plus V2 plus V3. You also have 1 plus I2 plus I3, because you're adding them in parallel, the currents add. So it's just recognizing, first of all, as a quick, easy answer to your question, which direction they add voltages, which direction they add currents, and make sure that you have enough in series and parallel, in aggregate or whatever, to get to those totals. Then the last bit, I guess, is the needed watt hour. So the watt hour is the multiplication of these, right? So volts times amp hour equals watt hour. So it's probably a similar kind of calculation. So if I have 4 volts and 1 amp hour batteries, and I need, 200 watt hours, the calculation probably ends up being the same, but it could be probably acquired any of a number of ways. If you have 200 watt hours, that could be what I just did before, which was 20 volts and 10 amp hours. So that would be 5s 10p. You could also do 200 volts by 1 amp hour, which is just like a ridiculous amount of batteries in series. What is that for? It was 20. So that's 50s 1p, which is like a crazy configuration, but you could, anyway, you could see how you could have multiple options here to get this done. Whatever, you could have 4 volts. No, I'm making myself do math here, and this is getting dangerous. What, 50 amp hours?
Yeah. Or
50 amp hours. Is that math right?
To get 200 watt hours?
No, 20, 25. No, 50. Yeah, 50. Yeah, 50 amp hours. 4 times 50 is 200.
Yeah, you want 200 watt hour?
4 times 50 is, yeah.
Yes.
So,
yeah.
So that's right. One. I'm doing like the extremes here is the point here. So this is 1s 50p. I guess S and 50 and 5 look too similar, so this is kind of messy. But hopefully you kind of understand here that it's just arithmetic. I mean, it's literally just like arithmetic. And then speaking more in depth as to which of these is better, I'm not. There's probably reasons why you'd want to have more in series or more in parallel, or not, or having them equally S and P kind of distributed. There's probably other reasons why you would or wouldn't want to do that. And then as it relates to a battery management system, if I'm sort of your first part, should I try to have close V to devices V? I think you're kind of asking about
like an electrical engineering question.
Yeah. Some of this is a little beyond my expertise of really programming systems this large or whatever. I can have high voltage, low current, or low current. Yeah, right. This is what I was kind of talking about, right? The arithmetic works out. You can have high voltage and low amp hours or whatever, or vice versa, right? The BMS can change voltage. So
what's BMS again?
Battery management system.
Battery management system. Okay.
So it's like the wrapper on top of the whole thing that controls it. So
okay.
All I can kind of say are some general things, reactive, and I don't know exactly how helpful or how much this you already might know, but it's like when you have a lot of batteries in series, you have an aggregate voltage, right? If you have 2 4-volt batteries in series, you got 8 volts, plus or minus when it's charging, discharging. But it's 8 volts, right? Well, it's great when that's 4 and 4. It's bad when that's 5 and 3. It's terrible when it's 6 and 2. And when it's 7 and 1, your battery's exploding. Like you can't have one severely overcharged and one severely over discharged. The more stuff you add without individual BMS modules that can control or at least monitor individual voltages, whether it's, if you have like 10 in series, whether, it's really cumbersome to implement a BMS that can monitor each voltage individually. A lot of times it's like, well, I've got 10 in series, I can monitor like sets of 4 or sets of 5. You know what I mean? Like I've got 10 volts here, I can measure 5 and 5. And then if I'm measuring 6 and 4, I know I've got a problem, because that's one of the things that can cause batteries and vehicles and battery packs to fail or have problems, is that when, you're charging and discharging, you want them all to go at the same rate, but there's no way for you to tell exactly, like, one half of it is, it gets, over time, you can have an unequal distribution of charge across your battery pack. And so that can be a problem, right? Current will follow the path of least resistance, or proportionately so. So it's like, if there's something wrong with one of your batteries where it has a soft short or there's some connection issue, and there's a higher resistance there, it won't be getting as much current going through it, so it won't be charging at the same rate. The other batteries will have to make up the difference, which means they'll get overcharged or over discharged. In, like, for example, in like a commercial electric vehicle, I don't know how the BMS works precisely. I don't know how many individual or how granular it's able to monitor and measure the battery health, or if it's more of an overarching thing. And if it detects there's some issue, it, will say, hey, don't drive your car because it might explode. I don't know exactly how this works, to be perfectly honest. But I know, generally speaking, the things that I just kind of talked about, which is that how you can arrange it, and then how granularly you can monitor with your BMS will matter, because you can hopefully detect when there's a problem occurring, because one part of it is overcharging or over discharging or what have you. So go ahead and comment more, Reactive, if you need a little more follow-up. That's kind of what I can say to that effect, I guess, if that's kind of along the lines of what you were asking, I guess.
I guess moving on, some of these we may be able to answer or not answer, but Tamiz is asking, hi, sir. Now I'm starting to work in supercapacitor. How to understand the mechanism and how to learn faster? I mean, he's not asking us to necessarily describe what the mechanism for supercapacitors are.
It's just, it's capacitance. I mean, it's just buildup of charge on the surface.
Yeah. I guess I don't know exactly how to answer this question. How do you learn faster?
Well, how do you learn faster? You sleep with the textbook under your. Well, so you
do a lot of experiments and keep failing.
No, it used to be you'd sleep with the textbook under your pillow, right? And that helps you absorb it. But now, all of the information in the world is on your smartphone.
That's right.
So if you put your smartphone under your pillow, you'll wake up a genius. That's how this works. Sorry, that's such a bad joke.
Or have severe anxiety.
That's correct. You might just make you more anxious. Yeah. Or I don't know.
Yeah.
I mean, all I can kind of do from a mechanism perspective is show you,
like, double layer charging.
Yeah, like how the double layer charging works. Like, maybe
we can show you. We can show you that.
I have this slide. It's something.
I never know whether or not supercapacitors. I feel like supercapacitors have to work by some other thing, because they tend to have pseudocapacitance.
Yeah, pseudocapacitance is hard to grasp, I think, isn't it?
They have all kinds of other things that are happening, but I mean, generally speaking,
it's this kind of a process, though. It's the double layer capacitance, which happens on a solid liquid interface, which is what is happening in a supercapacitor. And so you have an electrode, you have solvent, and you have ions. You apply a polarization, a potential at your electrode, which causes the surface to become charged positively or negatively, one way or the other. And so if you have positive ions and negative ions in solution, when your electrode is charged one way or the other, it's going to repel the like charges and attract the unlike charges. That action creates basically like a plane of ions of the opposite charge some distance away from the electrode surface. I'm extraordinarily oversimplifying this mechanism and procedure. There's an inner Helmholtz plane and outer Helmholtz plane. There's a lot that's going on in reality. But for the simplest kind of understandable explanation, you can look at this and say, I have a negatively charged plate, my electrode, a positively charged quote unquote plate, which are in this case potassium ions, some distance away from each other, separated by a dielectric material, which in this case is water. In a supercapacitor, sometimes it's water, sometimes it's some other material. I don't know precisely what they use in capacitors, but that definition is capacitance. It's a capacitor. A capacitor is basically two plates separated some distance with opposite charges, separated by a dielectric material. It's a mechanism through which charge is stored. So a supercapacitor is a charge storage device, and that is very, very simplistically speaking, the mechanism of it. So I guess that's kind of how we'll tackle that, and I guess we'll move on.
Mm-hmm.
So the next question is about supercapacitor stuff.
Yeah, it's just he just wants to know, can we speak on our view on supercapacitor research and where it's going? I think Veronica Augustin at NC State is the only person I know of who's doing like supercapacitor research. Not to say she's the only person doing it, but that's like the person who comes to mind. I would look at her work. I mean, I think a lot of people are actually just doing a lot of fundamental research. Maybe that's just because I gravitate towards fundamental research, oddly enough. But where's it going? I think people are still studying supercapacitors, but I don't know exactly where it's going. Do you? Or I don't know if we want to get to
that question.
I don't.
That's going to have to be a question answered by someone who's done a study of the literature of supercapacitors in the last 5 to 10 years, and that person is not me.
Yeah. I'm sorry we can't provide more.
Yeah, I'm not sure I know enough to answer that question, to be honest.
Yeah. Okay, so Ivan is asking, what does the difference between the half-wave potential and the formal potential say about the reaction's reversibility? I don't think it says anything about they're two different potentials. Sometimes I think some people use half-wave potential because actually, maybe you're right. When you have a kinetically reversible system,
the halfway
potential is equal to the formal potential.
Yeah.
If you have a system where it's
more irreversible,
like there's a coupled chemical reaction and you don't get a lot of the reverse wave, then the half-wave potential is just like an estimation, sort of say. It's the best thing you can get when you don't get that second wave of irreversibility. But I don't know if anyone has actually, like, if there's like statements about like, oh, if the formal potential is equal to X and if the half-wave potential is equal to Y, then it tells you that, oh, your system is irreversible. It's usually about like the shape of the voltammograms, and when you do scan rate studies and things like that, to help you determine whether or not you have something that's irreversible. Because it's not to say that a system doesn't have a formal potential. It's just your ability to calculate it might
so
not
I
exist.
think I have some answer because I just tinkered with our software for a minute here, which is simulation, conveniently. And here's to that point. Here's a simple CV. Let me put back to where it started here. Here's a perfectly reversible CV, right? The standard potential, formal potential is 0. This is the CV right here. I'm going to try to make it a little bigger, right? Okay, great. The half-wave potential, halfway between the two peaks, is the same as it's a 0. It's all 0. Everything is the same. It's nice and reversible. Okay, let's make this very not reversible. So I'm going to basically slow down this kinetic constant. Is that roughly the same as making it not reversible? Or it's just, I guess it's still
it's reversible. Just making it kinetically slow. So I guess I'd have to, which is fine. I mean,
it's a similar kind of situation. I think this will answer kind of the question. It's not exactly the same. This is kinetically slow. Yeah. But let's pretend this is kind of the same kind of. With irreversibility, I'd have to change the mechanism a little. I'm not going to tinker too much. Here's the point, though. In some situations, I think you could end up in it where, okay, there's a bigger split here, But if you just take the half wave, it actually probably ends up right at 0
It'll
still.
be at 0 again, yeah.
So one way for me to make this not that way is to change the diffusion coefficients.
Yeah, that's
So
true.
now the half wave will be minus somewhere in here, but the formal potential is 0. So I think part of the answer could be that if there's a severe difference between the formal potential and the half wave potential, it means that there are differences in that it's possible, not possibly irreversible or pseudo reversible, or it's not that reversible. It's somewhat asymmetrical, or there's differences in the transport patterns of either side.
Yeah.
I think those are some possibilities for what could cause that.
Yeah.
Just based on that very brief kind of depiction using the simulation there. So.
All right. So just I guess going back in order. Meliodas, let's see, he's asking, if I do an EIS experiment at different potentials, say once at the OCP, again at the onset potential, and then one more at a more positive or negative potential than the onset, I guess
getting different plots for all the potentials.
And I'm getting different plots for all the potentials, then which should I take as the correct one?
This is my triggering thing again.
Yeah, no. What you got is the result. You do get different Nyquist plots and different EIS results at different potentials. That's the beautiful thing about EIS. You don't get just like one Nyquist plot that rules them all. It's like, oh, at different potentials, the charge transfer resistance is different. At different potentials, the nature of diffusion is different. The double layer capacitance, or the frequency of the double layer capacitance happens, is different. So it's not to say one's correct and one's not correct. One represents the EIS at a specific potential, and one represents the EIS at a different potential. So that's kind of the answer. There's no correct or incorrect. It's just what it's assigned to. Done. Nice.
Yes.
I must have missed this from Ivan, from Ivan's previous thing, because I feel like Melodas's question was interjected into the middle of it, but maybe he didn't actually do that in
from a scan I obtained the peak current voltages, therefore half cell potential. I mean, this is related to the last question.
Yeah, I think it's related to the last question.
After some calculations including diffusion rates, I've got slightly higher form. Yeah, I think that's kind of answers my question. I didn't even see this, but I sort of simulated my way into the same conclusion, which is different diffusion rates for like the product and reactants can lead to discrepancies between formal and half-wave potentials. So that is observable. And it is one explanation for why those can be different, or different diffusional rates.
Yes.
So,
yes. Okay, moving on.
Yes.
Hanzo, I'm getting a question from Hanzo is the next one.
I think so.
All right. Hanzo is asking, can one determine if a metal is immune by looking at a Pourbaix diagram for the specific metal? For example, nickel as a coating on 304 steel in a KOH solution under high pressure O2. Well, Pourbaix diagrams don't say anything about pressure. They only tell you about the potential and the pH.
Yeah.
And you're probably not going to, and they're not going to give you mixed results about like nickel on 304 steel, which has a lot of things. Pourbaix diagrams. You can of course create your own Pourbaix diagram, of that system, but you cannot. I don't think you can just look at a Pourbaix diagram and then determine, oh, this reaction is not going to occur.
I think the best you could do is get a hopeful, for example, conclusion. For instance, something like, well, if I want to use nickel as a coating on my 304 in KOH, so I know the pH, at these potentials, probably it'll be the nickel 2+ state, or it'll be nickel hydroxide in that particular, that's what the Pourbaix diagram is telling you. What phase will it be at what potentials and what pHs? But that's sort of just nickel itself. Something else might happen in conjunction with another metal. Possibly there's some unknown here. And it doesn't say a whole lot about high pressure. I don't know The Pourbaix diagram does not give any indication as to what will happen at pressure. But in a very general sense, I think that you can get some indication as to what state, like natively, the nickel would be in at those pH and potential combinations. And the follow-up here looks at no reference electrode in the solution, just the potential between 304 and pure nickel. Again, yes, in theory, but the high pressure is not something the Pourbaix diagram speaks to. So there's some unknown there. You probably just trial and error and see what happens yourself. Frankly, because I don't know that you're getting information about the pressure or the oxygen presence with respect to the Pourbaix diagram.
I'm also a little confused because you said, all right, no reference electrode in solution, just the potential between, but you described nickel on 304 steel. So you're looking at just the metal-metal interaction, right?
Guess.
Is that it?
I guess. Well, it's got to be in
because the
solution,
KOH is
pH.
outside of because KOH is outside.
Yeah, it depends how well
solution.
Covered the surface is.
That's right. It depends how porous. Is this a fully formed layer,
substrate interface, whatever.
Yeah, at the interface. So that's another thing. But yeah, and this would still, even if you didn't have a reference electrode, the diagram still applies for how does the KOH interact with these different things, different pHs. Okay.
Varun has a question. I'm not sure if you mean DFT or DRT, to be honest. So if you're asking about density functional theory, I can't help you there.
Yeah.
I've never done DFT. I did more practical research when I was in graduate school or as a postdoc. I didn't do a lot of the theoretical numerical crunching DFT type calculations or analyses or modeling. Let's just say, I guess that's beyond my expertise. So I don't know if you're asking about density functional theory, like DFT impedance stuff, or you mean DRT, which is the distribution of relaxation times. That's a different thing. I can talk a little bit about that, but I'll leave it for now because I actually don't know. I'm not going to talk about something if that's not precisely what you've asked about. So I think I'll leave it there. And Varun, if you are here and you have a correction, please let us know in the chat. I'll check. But we're going to move on for now. I don't know if you mean DFT or DRT. So reduction. So it's Melodios asked about, we talked about that already, the aluminum thing, and then the power density, we talked about that.
Yes.
So Calamedia is next, I believe. Do you know of any reliable reference electrode in organic electrolyte that would ideally be possible to make in a regular chemistry lab? I am currently using a platinum pseudo, simply a wire, but don't trust it. Yeah, platinum isn't necessarily the best choice, I think. I have been recommended LFP, lithium iron phosphate.
I have no idea.
I guess LFP in battery terms is lithium iron phosphate. I'm not sure if that's what you mean. There is proton vehicle present in the electrolyte, and I have a rather large cell potential.
Okay.
Let me think here.
So if you're an organic electrolyte,
you have to make it in your lab, right? Stainless something. Okay, so silver or some kind of stainless steel rod of some kind usually work pretty well. Stainless steel is relatively non-polarizable.
Most people use they usually use like an internal reference like ferrocene for organic electrolyte systems.
So then it's a 2-electrode system with an internal reference, right? Or do you use a silver wire also?
You could use a silver wire.
So then the reference electrode is twofold. It's a silver wire, but there's also the internal thing. But I think the problem might be if this is like a regular chem lab, maybe they don't have ferrocene or something. I'm just guessing. I mean, I don't know.
Right? I mean, ferrocene is a relatively inexpensive, highly available molecule that a lot of chemistry labs usually keep. But it's like organic electrolyte. Like if you're in acetonitrile or THF or DMSO, ferrocene is soluble in those solvents.
Yeah.
And then
how much do you use, like 5 millimolar, 10 millimolar or something?
Yeah, you can use 1 millimolar of ferrocene. It could just be a little tiny CV, and then like you can look at the whole, the rest of your window.
Yeah.
And you're right, like a platinum pseudo or a silver pseudo is going to drift a bit, but the ferrocene potential is the ferrocene potential.
Yeah,
so
you're correcting to the ferrocene
correcting
each
to that.
time.
Yeah. You
Yeah.
can do it before and after your experiment to see if your CV's drifted at all. But the difference between those should always be the same.
Yeah, and otherwise it's just hard to get and make consistently performing redox couples for non-aqueous. Like there's like silver nitrate, like you can get like like a nitrate salt that's soluble in alkaline, and then you could try to form like a silver nitrate couple of some kind. It's tricky.
Yeah, like a silver oxide or something like that.
Yeah, like you can try to oxidize the silver metal in the presence of some either oxygen or some other anion or something. It's hard to get consistency in those also. So I do think probably what Alex said is the best option. Get a silver wire or something, as your reference wire, or use the platinum, I guess. And get an internal reference like ferrocene for where you can adjust the voltage axis afterwards, or the potential axis. Yeah.
Yes.
Okay.
Tamoga is asking, just kind of going in order. What is electrochemical frequency modulation technique? Can I use it to get corrosion rates of aluminum anodes? I have not heard of electrochemical frequency modulation technique before.
Frequency modulation. I'm trying to see.
I think see if it has a. Let's see what it is.
Frequency modulation. I think I've seen this before. I'm trying to remember. It's been a while. Is this just multi-sign, or is it just a bunch of?
It kind of looks like it. A harmonic technique that relies on the non-linear nature of the corrosion reaction to extract information about the corrosion rate and Tafel constants. Two sinusoidal waveforms are summed and applied to a corrosion resample. The resultant current is recorded. I don't know enough about that.
Yeah, I don't know that I can speak to it either.
But we know another thing to learn.
Yeah,
electrochemical
modulation technique. I do think you can use it to get corrosion rates. I think that's what it's for, but I don't know how that works precisely. It's not a technique that I'm familiar with. It looks a little bit like what's known as the electrochemical noise. That's a similar kind of a thing where, it's basically just a ZRA measurement at a certain frequency. You just measure the noise and then you do kind of an FFT type of analysis on it, which is kind of what you're doing here with the frequency modulation, is that you're applying different frequencies and then you're deconvoluting the signal somehow to calculate the corrosion rate. Electrochemical noise is a similar kind of phenomenon. You're looking for peaks in the noise, sort of, and you're drawing conclusions about corrosion rate. But I don't know how to speak much more to it specifically than that. So I think we're going to leave it there. It's a good question. I do think the answer to your question is yes, but I don't know that I can say how.
Yeah.
Right. Any more than we've just mentioned there. So
yeah.
Okay. So Lakshmi, I think, is next. Could you please tell something related to hydrogen evolution using electrochemical cell and alkaline electrolyte? Well, we just did that. How to calculate the electrochemically equivalent surface area? Well, we talked about that too. So
a lot of these in the beginning of the live stream.
We might move on, I think. So I think, rather than answer it twice in the same, this is a YouTube video. You are watching this on YouTube. Rewind. Or LinkedIn. But when you are watching this later, right now I'm speaking live. But if this is later, there are timestamps down below, and look for the timestamp where it says something like alkaline HER and water splitting or something. I talked about it a lot back in time. So move that little button and you won't hear what I'm saying next because you're going back in time. And then you'll see me talk about this. I'm like so meta, right? I'm backing up.
Do you remember, not to go too off topic, do you remember the movie Spaceballs? And
it's been a long time.
And it's like, how are we going to find like the princess and the person? It's like, I know. We can look at the movie right now because it was like straight to release. So they put the VHS in and then they fast forward to like right now. It's like, when does this happen in the movie? Right now. Wait, and they're like looking back and they're seeing.
It's like so self-aware.
Yeah, I know. It's like, when do we pass them? Just now. Now. How do we go from now to then? We missed it. When?
Then.
Just now.
Just. It's like a who's on first thing.
I know, it's a who's on first thing.
So brilliant.
Yeah. Okay. All right. Sorry. Wild tangent, but that just reminded me.
Well, that's exactly what I was doing.
Yeah.
Then is when I talked about it. So go back and see it then.
And if you're watching this now, which is later, but in the future, you would go back later.
Go back later. Then. Go back to the future.
Back to the future.
If you rewind at 88 miles an hour.
We're talking to you in the future right now.
This is getting trippy.
Okay,
this is getting trippy.
This is getting trippy.
Joaquin is back.
Good to see you, Joaquin.
Yes. How can I use EIS to evaluate whether a chemical reaction is occurring at an interface, for example, solid-solid? Could I determine the reaction rate by modeling it with an electric ECE?
Or cyclic voltammetry.
No, I think that's just the.
Oh, he's using
that's the emoji. Yeah, the emojis don't come through in our other software, but I think that's just. That's
that's
thing. In theory, I think so. So if a reaction is occurring at an interface, a solid-solid interface makes it a little bit trickier. I think the frequencies you'll have to use will be a little bit higher for solid-solid interfaces. But in theory, if a reaction is occurring, you would get, I mean, in the simplest, expectation would be a semicircle at high frequency or something, or near, I'm guessing for a solid. And you could just use a void element or a Randall's element to model that. The reaction rate would be, you could very loosely just propose that it's related to the charge transfer resistance that you measure there. I mean, you could do, like, for example, RCT is equal to RT over NFI. So you could get to a heterogeneous rate constant through basically correlating the charge transfer resistance to kinetic current at different potentials. And then you could extract in a Tafel plot like manner. So there is some modeling and kind of, procedure by which you could correlate the charge transfer resistance if a reaction rate is occurring to the heterogeneous rate constant and get some kinetic information. So that is in theory possible, but first you have to do the experiment and see if you see like a semicircle effectively, right? Or some sort of impedance response that is indicative of a faradaic reaction.
Yeah. It's interesting because it's like he's using the CV thing. He's also saying ECE, which I always think about as like electron transfer, chemical step electron transfer.
Oh, I thought
that's the thing I'm trying to like. But he also said solid interface, and I'm like,
I just read that as equivalent circuit. Maybe he means an ECE reaction.
Oh yeah,
maybe. I don't know, maybe it's an ECE reaction. I don't know. I just read that as equivalent circuit. Sort of. I don't know. But in general, I don't. Yeah,
I think we need more information.
Yes, I mean. I think if you're just talking about impedance, what I talked about.
Yeah, that's right. Yeah. You would think that, but okay. All right. Yeah. I got confused.
Okay.
I'm sure we get, Joaquin, let us know more.
Yeah, if you need to follow up there.
As we have time, which we're very quickly running out of.
Yes, but we're trying to get to everything. There's only a hand. We're getting close to the bottom. I can see.
Yeah.
Akash, I think, is next.
Yeah, right? I think Akash is next. All right. So Akash says.
We did the same thing.
We're
fighting over it.
Yeah.
Okay. While doing EIS fitting with circuit, how can we confirm the perfect fit-in parameter to consider? Only by looking at the curve. Okay.
And then
I'm not sure if this is the follow-up question is related. Also, while doing EIS analysis like electrocatalyst HER, in all data, I'm getting inductance, position Z, imaginary, how to avoid it. Well, if you're getting inductance at high frequency, just don't do those high frequencies. High frequency inductance is just from cable effects and things like that. It's irrelevant. Nobody cares about your high frequency inductance. You don't have to fit it and you don't have to show it. So if you're going from 1 megahertz to 1 hertz or 0.1 hertz, and you're getting a lot of inductance from 1 megahertz to 100 kilohertz, just start at 100 kilohertz. Nobody cares about your inductance. It's not relevant to your information, to your data, to anything. On the other hand, if you're getting inductance at low frequencies and you're getting some kind of a loop or a curl or some other weird behavior, you probably can't avoid it. It's probably something that's intrinsic to your system, and that's a whole different discussion, but you can fit it, and then the inductance value means nothing, and it makes Alex really upset, and it makes me
slightly happy.
clipped forever into oblivion about values meaning nothing, and that's another inside joke. In any case, if the inductance, as I suspect, is just at the high frequency, don't worry about it. Just ignore it. Move on, move to a lower frequency or cut those data out. It's not relevant. You're not missing anything. HER is not really occurring at those frequencies. You're not losing anything by cutting out the high frequency there. And then as far as how to get the perfect fit, I mean, usually it's find a bunch of different circuits that might apply to your data, fit them and compare the error statistic across each of them. So you fit circuit A, and then you fit circuit B, and then you fit circuit C. One of them has one void element, one of them has two void elements, one of them has 9 different elements in a transmission line and a Warburg element and all kinds of crap, right? Or whatever. So you fit, and you have a reason for why you've chosen these circuits, have them theoretically representing the interface and the faradaic reaction, the double layer buildup, whatever. Have reasons why you're picking the circuits, but then some of this is the effectiveness of the software that you're using, of course, but you will get some kind of error statistic, chi-squared or some sort of goodness of fit, depending on what your software is you're using. If all things being equal, whichever one has the lowest good, error statistic, I guess, and if it looks the cleanest, like it's tracking the data well enough, that's probably your best answer, your perfect fit, quote unquote. So,
okay, we're running low on time, but I think we can get through.
We're gonna do it. I believe in us.
Get through a few.
I think we can do it.
Chris is asking, is it possible to detect a degraded cell within a series connection of 5 cells using EIS? I think the answer is no.
No, it's yes, but it's not clear how.
Oh.
So yes, you could.
Oh, in principle you could.
Yeah, in principle you could. It would be difficult to know which cell is the problem, but impedance can absolutely be used as a diagnostic for detecting degradation or failure or state of health problems. If you're not able to, similar to the battery management discussion I had earlier, if you're not able to isolate your impedance measurement to individual cells in series, all you're going to be able to do is determine there's a problem because empirically my impedance results fall in some range that is problematic or indicative of overheating, overcharge, whatever. But it will not likely be easy or possible at all to determine, well, it's cell 3 out of 5 that's causing the problem. That will be very tricky to determine. But yes, impedance is a tool that can be used to detect state of health of batteries. Actually, that's what I did my postdoc on.
Okay, going through. Santiago is asking, okay, thank you for the answer. One question, should constant current be applied with chronopotentiometry, or is it charge and discharge process? So Santiago, I believe when you were asking your question originally, you were talking about nickel deposition or just some electrode deposition. That should be done with chronopotentiometry. Charge discharge is usually for battery techniques, which I don't think is what you were interested in. So for electrode deposition, chronopotentiometry is the way to go. All right, Akash is asking, suggest best free EIS circuit fitting software. Well, we don't have free. We have our software, which is very inexpensive. You can get a basic license, which can almost do everything.
It does everything
for $20 for a month, and that's usually all the time you need to do it. And we showcase it on our live stream pretty regularly. And so yes, it's not free. I'm sad that we've made a lot. We continue to upgrade the software, and that has a cost associated with it. But But yeah, if you log in and you sign up, it's
yeah, this is it right here. This is the basic monthly license for our circuit fitting. It's $20 a month.
Yeah, that's it.
And
you get a discount if you buy it for a year.
Yes.
You know?
And these are the features that it gives you compared to the different licenses. Basic gives you basically everything that you would need, and there's a few fancy features the research license gives you, but the basic one is definitely sufficient.
Yeah.
So that's the best we can tell you for what we have. There's probably some freeware out there. I don't personally know of any at the moment. I did years and years ago. I don't know anymore if there's any free impedance like circuit fitting stuff anymore. But anyway.
Yeah. Sorry. Okay. Do you want to deal with this next question?
We can.
I feel like this is a question that probably end with, considering
we'll end with that one.
We'll end with this one. Don't worry. I know people have a lot of questions. We will save them for next week.
We always do our best to save it, although we still have some that it's a building up here. We do our best to get to everything. Yeah, we certainly have a lot here. Okay.
So
Akash had another. Let's see.
Oh, you wanted to go to Akash's
I don't know. Did you already? Okay. You just answer this? Oh
no. But Win has a question about imposter syndrome during the PhD journey.
Oh, was that what we were going to answer last?
Well, because if you wanted to,
I mean, it's kind of like therapy session. It's
it's an ending therapy session for the last like 5 minutes.
I guess, yeah.
If you want to, we can skip it and go straight to or I mean, granted, being able to answer the rest of these in a short time frame is not going to be easy.
Mm-hmm. This is easy answer.
Yeah.
So Nyquist plots should be represented in an orthonormal axis. Most published articles ignore this. Which ones? They should not be ignoring this. I actually have totally changed my opinion of this. I used to not care at all, and now I am like militant about it. It's very important to plot orthonormal axis with Nyquist plots. It's the appropriate way to view Nyquist plots. The axes should be the same, and the main reason is that the features of most interest on Nyquist plots, things like semicircles, vertical lines, or 45-degree lines, cannot be viewed as such unless the axes have the same scale. You cannot quickly determine, is that capacitance or diffusion? Is that an actual semicircle, or is it a non-ideal semicircle? None of those things are able to be determined quickly with your eyes unless the scale of the X and Y axes are the same. It is critical. Frankly, I used to think, oh, who cares? It doesn't matter. And then I'm like, oh no, I was very wrong. I've changed my mind. I don't personally think, if I were the emperor of scientific publications, I would not permit a paper to be published without orthonormal axes. It's my personal opinion. So you asked for my opinion, and you unfortunately got it. I'm feel very strongly about this now. I do think it's very important. Okay. Should we get to therapy session? And we'll
sure. Yeah, we can get to therapy session.
Okay. Yeah. Win has a good kind of general question here. I have unrelated to electrochemistry. I don't know if you have imposter syndrome during your PhD journey. If so, what did you do to cope with it? I mean, I don't know. Do you want to go first?
Oh yeah.
As I kick it to you. Yeah.
Did I have imposter syndrome? I guess when I first entered graduate school, I went to like a small school for undergrad, and so when I went to graduate school, which is a bigger university, and I had all these people from it's like, oh, I went to like MIT or Harvard or wherever, come to graduate school with me. It's like, oh my God, like all these people are super smart. And like, what the hell am I doing here? And so starting the PhD program was very much like drinking from a water fountain, or not a water fountain, a fire hose. There was tons and tons of information. There was a lot of stuff that I was just like learning very, very quickly. And truly, to a certain degree, I kind of just I was just too stubborn. Like I didn't quit. I just I wanted I always wanted to know what it was like to be a PhD. What is the next level of understanding in chemistry, after my undergrad. But yeah, the imposter syndrome is like, oh, you don't belong here kind of thing. And yeah, you run into that. But
I feel like I also met a lot of people who were struggling the same way as I did. And I had to very quickly mentally remember that, hey, somebody else has a different project than me. What they need to do to finish their PhD requires a different time commitment, work effort, things like that. Like organic chemists necessarily had to spend like 12 hours in the lab because they just had so many reactions they had to run and work up and all this stuff. But you know, if you were a physical chemist, which was the lab I joined, you know, you would spend like days just like, okay, I put the sample in a vacuum chamber. I have to pump it down for 5 hours. Then I have to do a deposition. Then I got to wait. Then I got to incubate the sample. Then I got to align my laser. And then, and then like 2 days later, when everything's ready and the laser's aligned, and you put your sample together, you collect your data in 2 minutes. And it's like, God, I spent like a week preparing the sample to collect 2 minutes worth of data. That was what my life, that was like what my life was. But yeah, like I guess I never felt like I was an imposter, sort of say, that I didn't belong. Like I didn't observe that there was like a massive difference in like skill or intellect between me and my peers, especially as time went on. Like I learned a lot of stuff like more quickly over time. And but when it came to electrochemistry, I definitely did not I never felt like I really, really, truly like understood it. I mean, it wasn't until I was working here at Pine that I really started to learn a lot of electrochemistry, like what was actually going on in detail. So I don't know. I think when it comes to imposter syndrome, it's like I think you can I think you can always outwork the feeling. It's like you feel like an imposter because you don't know something. But if you know something, or if you've done enough experiments, or if you've, you know, done enough work and you've compared it to what was done in the literature, you have an overwhelming amount of evidence to say that like I know what this is. And you can just say like, hey, like I either published this or all these other people do this in the literature, and I'm doing the exact same thing, and I've done this before, so I don't have to feel like I'm an imposter, sort of say. So yeah, that's how I cope with it. You can kind of outwork the feeling. That's my 2 cents.
Yeah, I'll fill mine. I wanted to just get to this. Halamedia followed up. I'll just briefly say one thing about this, as it was a follow-up from the question about adding the internal reference. Basically, the point was, I can't tolerate much drift because I want to be able to trust my impedance. Ferrocene sounds promising. The only issue is that SEI forms on the counter electrode. I'd be concerned with introducing new species into the system that might alter the SEI formation. All I can kind of, so I find it I think that's a valid concern. I find it unlikely that ferrocene would interfere with an SEI. Just intuitively, I don't think it would. However, there's a very simple kind of a thing here. It's just a simple trial and error, honestly. Do some CVs with a silver wire as your reference or whatever. No ferrocene, see what it looks like. Add ferrocene, see what it looks like. If the only difference across the board within reasonable error is that you get a little ferrocene duct somewhere in there, it's probably a decent indication that it's not impacting the SEI or anything else, and that it's just providing you a reference. And then really what you're doing is, because the EIS might take a while, I understand you're concerned about drift. You can't avoid some amount of drift in impedance no matter what. But take a CV, figure out where the ferrocene is, apply a voltage, do impedance, take a CV again. You might have to sort of average and assume, there might be some drift. You might not be able to ever get away from that. But if you have ferrocene to sort of recenter things, hopefully the applied potential you use for your impedance, you've done just after you've done a CV, you've located where the E0 is or the potential you're after, you can kind of adjust things as close to in the moment as possible. These are the trials and tribulations of using non-aqueous, I guess, to a certain extent. So
yeah, that's true.
We'll end with this. I'll just sort of opine a little about this as well. For me, it's a little different. I would sort of break this down into 2 categories. One of them is things are hard. My data sucks and I hate it here. The second is I feel like I don't belong here because I feel like I don't know enough. Those are kind of different things. For me in graduate school, my first 2 years were the first one, not the second one. I didn't feel like I didn't belong. I just hated it. My data was terrible. I wasn't getting anywhere. The last 2 years, 2.5 years of my grad school was like the best years of my life. I loved it. And that's for a variety of reasons. But I didn't really deal with the imposter syndrome, so to speak, until I was a postdoc and then in my current job, if I can classify it as imposter syndrome at all. That, took the form, for instance, of being in a group as a postdoc and being the only person with electrochemistry experience or knowledge. It's a weird phenomenon having just, in my case, having finished my PhD in chemical engineering with, focusing on electrochemistry, and then everybody looking at me like I'm an expert in electrochemistry. And like, I just finished my degree and, I know some things about electrochemistry, but like I'm the expert. And to be called an expert in anything is still weird to me. It's weird to be thought of as an expert. I mean, the same thing happened here I've been at Pine now for 10 years and I'm pretty comfortable in my job, I suppose you'd say. But like when I started here, I was hired for mainly because I have experience with impedance spectroscopy. Was when I was hired at Pine, 10 years ago, we didn't have impedance potentiostats, like capabilities and everything. So I was hired to help my company develop that, which we have now. And so I've been looked at for my entire time here at Pine as an impedance expert. And it's still kind of weird to me. Like I don't, that's kind of the imposter thing, I guess. Like, yeah, like, oh, I'm an expert. Like, I don't know that I'm an expert in anything. Like it is bizarre, kind of thing. I think Alex nailed it though. I think the answer to imposter syndrome or despair, depression, feelings of doubt, anything of this nature mentally, most of it's mental, right? I mean, it's mostly mental, it's mental health, it's mental kinds of just trials that we all kind of go through to various degrees. But the answer to that is action. It's not inaction. It's work. It's go outside. It's like our thing from going outside.
Yeah,
right?
going outside.
Our funny ad in one of our podcast episodes. Yeah. But I'm serious. Like exercising, physical exercise is often a really a remedy to sort of getting yourself out of a mental funk.
Yeah.
Go outside and you don't have to like run a marathon. Like I hate running too. I hate it. I like playing basketball. That's my exercise. I don't like running for the sake of it. Like, go outside and walk, lift weights, do something physical, even if it's not like exercise per se, do something physical. Work yourself out of it. Hard work will be often like it's a way to train your mind out of some of these. Now I know that I'm speaking very broadly. Obviously everybody's specific situation or mental, situation and is their own business, right? Obviously. And everybody's got extenuating circumstances. I'm not trying to say, I'm not trying to say like, oh, if you don't do this, you're this or that. I'm not trying to make, broad accusations or anything like that. I'm just, in my observation and my experience, and frankly, psychological literature bears this out. For instance, these kinds of things working and it's like basically the more you give in to those feelings, and I know some people with anxiety, it's a similar thing. It's when you feel anxiety or you feel imposter syndrome is basically like a form of anxiety. I don't belong here. This isn't right. It's irrational, right? You can't really rationalize it. So you can't necessarily stop yourself from thinking or feeling these things. That's not the name of the game. You can't stop your brain from what it's doing, but you can control your actions and you can control what you do. You can control, well, I feel this way, but I'm not going to act in accordance with the way I feel. The way I feel is very bad. I feel like I should quit. I feel like I shouldn't be here. I feel like whatever, right? Well, I'm not going to act that way. I'm going to act as though I know what I'm doing, or I'm going to at least work until I do feel like I know what I'm doing. I'm going to choose to go and do things that will benefit me mentally and physically, rather than give in and wallow in my despair, which will be that's a spiraling kind of a thing. When you feel the anxiety or the things of that nature, the temptation is to give in and say, well, whatever, I'm useless and I can't do this, and then act in accordance with the idea that you can't do this. And it's like, choose to believe that that's not true. Choose to believe that you aren't an imposter. Choose to believe, or at least act, that I can do this. I can work myself through this, right? You're in graduate school for a reason. You have the job or the position that you have for a reason. So that's kind of I guess the I don't know, pep talk that I would give to that. And it's really the same thing that you said. It's work yourself out of it, or work yourself into the mindset where you start to, it's like this phrase, fake it till you make it. I actually love that phrase because I actually think it's true. Here's my conspiracy of the day. I actually think that there's literal truth to the phrase, fake it till you make it, because tell me, what is the difference between fake it till you make it and practice makes perfect? What is these are like common English American, if you're not perhaps American English colloquial phrases, apologies, right? But like there's the common phrases like practice makes perfect. Practice a skill or a thing and then you'll get really good at it, right? And then fake it till you make it is like, well, I'm just going to pretend that I'm good at this, or I'm this or that, and then you will eventually become that thing. There's no difference between those two phrases, right? And it's like, the reality is that the beginning stage of that is that you are not good at the thing, or you are not the thing yet. Now, if the thing is like, I want to be an astronaut, well, I'm not going to make it. I'm not, okay, I want to be in the NBA. Well, I'm not going to make professional basketball player. It's not going to happen. I would love to, but I'm too old and I'm not good enough at basketball. Fine. Okay. There's limits to this. Okay. I get it. Fair enough. But like, again, if it's like, I want to be a competent researcher, or I want to be good at my job, or whatever. These are things that you actually can fake it till you make it, or you can practice makes perfect, whatever the, cheesy analogy is. I do think there's reality. Your actual being and your performance and everything will follow the direction that you point yourself in. And you do that by working towards it,
Yeah. I guess, no, that's right. And I think the imposter syndrome it shows up when there's kind of like an uncertainty about doing something. But like, I'll tell you now, Neil does not feel, you probably don't feel any imposter syndrome about tying your shoes. None. You've tied your shoes probably thousands and thousands of times. So like, there's not a doubt in your mind that like, if someone gave you a pair of shoes,
good Lord.
you've been rocking the Velcro all this time.
Oh yeah. Gotta love that sound.
But yeah, I'm just like, I've done like hundreds of cyclic voltammograms. And so like when I see a cyclic voltammogram, like I just know, because I've seen hundreds of them. But if I'd only seen like 2 in my lifetime, then it's like, oh yeah, I don't know how to interpret this thing. If you gave me a mass spec, I'd be like, kind of. I don't really like, kind of. I remember that like, oh well, these are 2 isotopes that look like this, and that's about it. But yeah. So it's just like doing a lot of these and comparing it and like outworking the doubt, sort of say. So anyway, that's it.
It's a good question though. I like these kinds of questions because
especially to end the day too.
Exactly. Hopefully we end on a side note. And actually, this is the best question to end on. If you could learn electrochemistry again, Pine Research's YouTube channel.
Yeah.
That's my answer.
Yeah.
And with that.
And with that, also, if you are in San Diego, we are going to the ACS San Diego meeting
next week.
That's next week in San Diego. Yeah, spring meeting. So stop by the Pine Research booth, and we'll be there. Yeah.
Both of us.
It's
gonna be a good time.
Yeah.
So until then, we will be here next Friday as well because we're dedicated. That's how we go. That's how we roll. Anyway, I hope everybody has a good weekend and a great week. And thank you all for the questions. Hopefully we got to everybody. We did it right here.
Yeah.
It's been, it was a lot. We did try to get to everything, and take care, everybody. Hope you have a good one, and we'll see you next week.